This is lecture 8.1, which is your introduction to equilibrium and to Q and K, the reaction quotient and the equilibrium constant. Please make sure that you've taken care of the learning targets before you watch the rest of this video. There's also a really short video that I put the link to. It's this video, this YouTube link that I put the link to in the learning targets on Canvas. So make sure that you've watched that. I think it's really helpful to give you a conceptual idea of what equilibrium is. Okay, so let's see what we can do here. So as you learned in the nickel reaction, a couple of things about equilibrium and the activity where you were looking for when to stop your reaction was when the reactant and product concentrations became constant. So this is something that's really, really important. From the nickels and from the aquariums in the video, you can see that these graphs would represent that when the graph when the rate of reaction, in other words, the concentration over time stops changing, becomes constant, then what's happening is that we've reached equilibrium. You can notice that there's lots of different ways to look at this, but you want to definitely pay attention to the idea that in this first graph here, at equilibrium, there are more products than there are reactants. So we would say that this is a product-favored reaction. In this last graph, they're almost equal, but not quite. There are more reactants than products. In the top graph, it's a lot more reactants than products in graph B. And so we would pretty much say that this reaction really might not occur. And that would be a way of saying it's reached equilibrium when it's really reactant favored, which in last year's terms would have meant that it didn't react. And then in graph C, notice that the reactants pretty much go to zero. And so in this case, this reaction, we would say pretty much goes to completion when it reaches equilibrium. So all of these are kind of options as to how this can occur. And the idea of where it settles out at equilibrium in relationship to how many products compared to how many reactants is based on who your reactants are and who your products are and who the reaction is. It's not based on how much you start with. It's not based on temperature or catalysts or anything like that. So the nature of the reactants and products is what determines where the reaction settles at equilibrium. A few quick notes that you should already have in your learning target notes would be that equilibrium is a reversible reaction, that when we start out, the rates are not equal. Like this is a really fast rate and this is a really fast rate, but they're not equal. And eventually what happens is that it reaches equilibrium and the forward reaction is equal to the rate of the reverse reaction. This means that when it looks at equilibrium, it looks like nothing's happening. It looks like your reactants and products are constant, but they are not reacting. So you still have the same rate going forward as reverse, and so because of that, there's no net change. That's really, really important. Technically, in that nickel activity or in the aquariums, you could keep going forever at that forward and reverse rate being equal, and nothing would change. The equilibrium relationship is something that is mathematical, and I think that you'll really like working with the mathematical piece of it. It's pretty logical, so we will look at that as we keep going. What equilibrium is not is that the amounts of the reactants and products are equal. This is really important because sometimes equilibrium in definitions, people want to think that means it goes until they're equal amounts of each. But notice in these graphs that I have here that really only in one are they even close to equal. So this is definitely not a piece of the definition. And equilibrium is not that nothing is happening. And we call it dynamic equilibrium because it's still a constant reaction. It's just that there is no net change. Okay. So let's move on and talk a little bit mathematically speaking. We can refer to how the extent of the reaction and how the relationship of products and reactants works by using the equilibrium constant. And that equilibrium constant, your book does a lot of derivation to show you how it comes from the ratio of the rate laws of the forward and the reverse reactions, right? And they're set equal to each other and solved for K, and then you end up with this equilibrium constant. So the rule would be that you're going to take your equation and products will end up in the numerator and reactants will end up in the denominator. And just like when you're in an elementary step, the coefficients become the exponents. And so even though we're doing this for an overall reaction, we can definitely include them like that. I do want you to notice that this top equilibrium expression here is a Kc, which means that everything is given to you in here in molar concentration. And remember that we write molar concentration as these brackets. They mean molarity. Okay, so make sure that if you're writing the Kc expression, you use those brackets. Sometimes we can do this in rather in pressures, partial pressures, instead of in molar concentration. And so that would be what we call a Kp. So notice that Kp is putting this in terms of the pressures of gases. So this is really, really important. Please notice that these are P's and that there is no bracket here, because technically if you were to write this with like the partial pressure of ammonia inside those brackets, you'd be saying the molarity of the partial pressure. So it's really important that you, when you're doing KPs, that you do not put brackets in. You have to use the capital P to refer to partial pressures. There's one other thing that comes in that's really important, and that would be that the equilibrium constant expression does not include solids and liquids. It only includes gases and things that are in aqueous molar solution. So this is because of, your book explains this as well, but it's because of the huge amount of solids and liquids in comparison to the pressure of a gas or in comparison to the molar concentration of something. And so because we're looking at the overall change in equilibrium or concentration, as it reaches equilibrium, there's really not a very large proportional change in the concentration of a solid or a liquid. So when we write equilibrium expressions, it's gases and aqueous solutions only, and then it's products over reactants, and the coefficients become exponents. So kind of get used to that process. And if we're using molar concentrations, we call it Kc, and if we're using partial pressures of gases, we call it Kp. All right. The two are related to each other, but one is molarity, one is pressure in atmospheres. And so the idea would be that we could use the ideal gas law to come up with the relationship between them, but that would be an awful lot of work. So instead, often what we use is, if we need to mathematically determine Kc from Kp or Kp from Kc, we use this equation, which should be already in your targets. Note that R is truly the gas law, ideal gas law constant R, 0.0821 or 0.08206. 0.08206 if you need more significant figures. And the change in moles of gas is the delta Ng. All right, so this would be the moles of gas only in the products minus the moles of gas in the reactants. And we'll do a problem in a second that shows you this. So let's see what we can do. Ammonium carbamate is a solid that decomposes and forms ammonia and carbon dioxide gases. So we're going to do a problem that's related to an equilibrium problem here with this. And they tell me something really important here, that at equilibrium, I have these pressures and this amount of solid ammonium carbamate. Okay, so the key here is, it's really, really important, is that they're giving you these pressures at equilibrium. This means that I can substitute those values into the equilibrium constant. If those pressures are not at equilibrium, then I can't substitute them in. So if you're writing an equilibrium expression for your constant, any numerical values you use to calculate that have to be while the reaction is at equilibrium. All right, so part A says write the balanced equation. So if you want, you can do this on your own. Stop the video and restart it. Let's see. And this is a solid, and I definitely need to know that as I'm working an equilibrium problem, because remember that solids won't go into the equilibrium expression. And then I'm going to have my double arrow. And often, actually, let me show you. Often we write these arrows like this because it's faster. Okay. And then I have 2NH3 and... oops, sorry, I didn't know the 2 yet. Let's get this equation written first. So we have NH3 and CO2 as our products, and I can balance this simply by putting a 2 in front of the NH3. So that balances the equation. We want to write the equilibrium constant expression for this. So this would be K, and since they gave me pressures in atmospheres, this is going to be a Kp. So again, products, that's the pressure of the NH3, and the coefficient becomes the exponent, and the pressure, partial pressure of the CO2, and the coefficient of 1 becomes the exponent, so I can leave it off. And the reactant would go in the bottom, but it's a solid. So because it's a solid, you can write over 1, or you can simply just write equals the pressure of NH3 squared times the pressure of CO2. So this would be the Kp expression, okay? The next thing is that we want to calculate Kp. So now I need to take my equilibrium pressures and substitute them into this equilibrium expression. So for part C, we're going to say that Kp equals the pressure of the NH3, which is here, 0.0961. And we don't use units in equilibrium constants, so you can leave the units off. Actually, that's kind of refreshing. And the 0.0451 for the pressure of carbon dioxide. And I can do the math, and I solve, and I find 4.165 blah, 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 times 10 to the negative fourth. I have 3 significant figures, so this would be 4.17 times 10 to the negative fourth. Notice that when I compare this to 1, that this value is less than 1, which means that when the reaction reaches equilibrium, the reactants are slightly favored. So you want to picture that this is a less than 1 value, so it's actually favoring the reactants more than the products, because my denominator would be larger to make that K value less than 1. So there's Kp. All right, and now they want us to calculate Kc. So we could do the ideal gas law and figure all this out, but I don't know the volume of my container. So actually, I can't do it that way. I have to use the formula that uses the relationship between the two. When I first learned this, I had a really hard time remembering which one went on the left side of the equal sign and which one went with the RT. So I remember that this is not alphabetical, that Kp, and you may want to write that down, is on the left, and it's not alphabetical. This is how you're going to have to remember that formula. And the delta Ng. So the Kp we just found, 4.17 times 10 to the negative fourth, equals the Kc that we're solving for, times R, 0.0821, times the temperature has to be in kelvins. So be really careful. So this would be 313 Kelvin. They already gave me that temperature. And notice that everything that they're talking about here is at the same temperature. That would be because temperature is the only thing that would change the equilibrium constant for a reaction. So each reaction has its own constant, but a temperature change would change the constant, but a catalyst would not, unlike in rate, where a temperature and a catalyst would change the rate constant. In equilibrium, only changing temperature changes the rate or the equilibrium constant. So I do this, and I can solve for Kc. And I need to actually put my delta Ng here first, so I have to think about what that is. Let's come back here to this equation. In the products, I have 3 moles of gas, and in the reactants, I have only a solid, so it's 3 minus 0. So it could be negative if it were the other way around, so be careful. So this is to the third. It's always products minus reactants. So now I do my math, and I get 2.45738, some more numbers, times 10 to the negative eighth. And I have 3 significant figures, so that would be 2.46 times 10 to the negative eighth. Notice that this is also less than 1. This is important as a verification that you've done this correctly, because if a reaction is reactant favored, it should always be reactant favored. So finding Kc or Kp should not change that. Okay? All right, so let's keep going. The reaction quotient is written and works the same way as the Q expression, as the equilibrium expression, or as the K expression. However, K is always at equilibrium, and Q is I don't know if I'm at equilibrium or not. So you write it the same way, products over reactants, coefficients become exponents, but it's not assuming that the reaction is at equilibrium. So you can substitute any values, any values. They don't have to be at equilibrium, not necessarily at equilibrium, okay? So this is really important because it's a really helpful way for us to figure out if the reaction is at equilibrium or not. It can determine if a reaction is at equilibrium or not. So in order to do that, you need to know that you're going to compare Q and K, and so you'll have to be given K, or you'll have to have already know K somehow, and then you'll solve for Q, and then you compare them. If Q is less than K, then recognize that that means that you have too many reactants because you divided by too much at whatever point in time you are in. Okay, so you divided by too much, which means that your reaction is going to have to shift to make more products if Q is less than K. If Q is greater than K, then now it means that you have too many products, that now your numerator is too large, and so the reaction will have to shift to make more reactants. So temporarily, or for until it reaches equilibrium, the reverse reaction in this case would be a faster rate for a little while. And then very seldom, but every once in a while, you find that Q equals K, which leads to no shift because the reaction is already at equilibrium. So it's already at an equilibrium situation, and the rate of each would be equal. All right, so let's talk about how this works. So sulfur trioxide is produced by this reaction of sulfur dioxide and oxygen, and they've given us a Kc. So remember that this means that everything has to be in molarity or molar concentration. And notice that in this case, they're putting in moles of SO2, moles of O2, and oh, by the way, also moles of SO3, which is our product. They're putting them all in the flask. And so in this case, what we're doing is noticing that the flask is 2 liters, not 1. So the first thing I have to do is calculate molarities of all three, because it's not a 1 liter flask, so be on the lookout for that. So the concentration of the SO2 at whatever point in time this is would be 3.4 moles divided by 2.0 liters, which is 1.7 molar. The concentration of O2 at whatever time we're talking about is 1.2 moles divided by 2 liters. So that's 0.60 molar. And the, sorry, that's not the O2. I just looked at that wrong. The O2 is 1.5 moles divided by 2 liters, which would be 0.75 molar. And the SO3 is the 1.2 moles divided by 2 liters, which is 0.60 molar. Okay, so now this is at some point in time, and they want me to tell them if this is at equilibrium or not. So I need to solve for Q so that I can compare it to K. So Q, in this case, it would be a QC because it's molar concentration, would equal from the equation products, the SO3 gas squared, over the concentration of reactants, the SO2 gas squared, and remember that the squareds are coming from the coefficient, times the other reactant in the denominator, the O2 with a coefficient of 1. I'm going to substitute in the molarities that I just calculated, so this would be 0.60 squared over 1.7 squared, and also over 0.75, not squared. And when I solve for, excuse me, when I solve for QC, I find that QC equals 0.16608, a bunch of numbers, which with my significant figures would be 0.17. So I need to now go back to the question so that I can compare Q to K. This is how I'm going to evaluate whether or not the reaction is at equilibrium and which direction it will proceed to reach equilibrium, which reaction rate would have to be faster for it to reach equilibrium. So the Q is 0.17. The K they gave me, the K they gave me is 4.2 times 10 to the negative second, which I'm going to rewrite as 0.042 because I think it's easier to compare when everything is in the same format. So this would be 0.042. which means that Q is definitely larger than K. So your trick would be that this tells you that the numerator is too big because Q is larger than K, and that's the products, which means that we need to proceed to consume the products. This is how you would explain it in a free response question. Or the reverse reaction rate is faster at this point than the forward reaction rate, which means that the reaction is going to proceed to the left. And you can see that this is kind of a little trick that if you put Q first and Q is greater than K, then finish your equilibrium arrow and that will tell you which direction it needs to go. You can't explain it that way. You have to explain it like this, but you can use this as your knowing or in the multiple choice. So at this point then we can say that no, the reaction is not at equilibrium and that it will proceed to consume the products, or the reverse reaction rate will be faster, or it will proceed to form reactants, etc., as it reaches equilibrium. So a quick summary of how you use Q is Q and K. If Q is greater than K, the reaction goes to the left or makes more reactants. If Q is less than K, the reaction goes to the right or makes more products until it reaches equilibrium. And if Q is equal to K, then your reaction is already at equilibrium and there will be no shift. So hopefully this has been helpful. You should be ready for class and we'll practice when we get together. Thanks so much.